All right, so you guys all have this assignment. 4 points for each. Really, you just need to produce some images. The most challenging part might be just running top-up and running the DTI fit after that to produce all of the images that you'll be using for generating these images that you have here. But these are the data sets that you would actually collect on the scanner. So you collect does anyone collect a lot of DTI? I know for sure Seraphina does. Anybody else really into DTI? Yeah, I know you are, for sure. So in our typical protocols, it's a little bit different for some of the more custom protocols, but in a typical protocol, and I know that they covered this in the lectures, you collect, in most cases here, a full phase encoded, we call it PE0 or forward, which is posterior anterior, where you get this sort of stretching at the front of the brain. This isn't the best example because it's a little confusing. It's a little compressed right here. Really depends on what slice you're looking at in the brain as to how much stretching or compression you'll see. And then you have the PE1 or anterior posterior. It's just the way that it's being collected, which causes this sort of compression at the front of the brain. What TopUp does is take those two images and run it through some processing to create basically an average of those two. It's trying to figure out what should the brain actually look like, and then it sort of forces everything into that configuration. It looks more like this. It doesn't always work perfectly. This one does look like it's a little bit smushed in the front, but it does look a lot better than this one. Pointy brain in the front, and this one. I'm going to pull up the actual data so we can look through it a little closer. I definitely prefer AFNI, although there are things that you can only do in FSL, but for now, I'm going to open AFNI. I also don't know that this is the best data set. It might be a little noisy as I was going through it after I uploaded it. It might be a little noisier than some data sets you have. I also broke my water bottle this morning getting out of my car, so if I spill the whole thing on myself, don't laugh. All right. So the data sets, let me go to the data set you actually have. Which one I sent.
This is the one that's already been top-upped.
This is the one that has not already been top-upped. This is the first data set that you pulled.
Okay.
And it's currently running right now in this directory, which is why there were some extra files in there.
Yep.
But it has not finished the top-up process. As the top-up process is running, you'll see these lines kind of appearing here. And as these values get smaller and smaller, and they'll go all the way to like 0.000001, you're getting closer and closer to the finish line. So here we're at 120. We've got a long way to go before this finishes. So, but this is the actual data here. Just a snapshot of the data. And these are our V0 or V0 images. There's no diffusion weighting. We collect in this particular protocol, there are 6 throughout the entire data set where there's no diffusion weighting, so you get this very clear looking image. When there is diffusion weighting, you guys have probably seen, we'll look at it now, but the data is much noisier depending on the V value. But this is our PE0, so in this case, that is what we call forward, and you get this sort of stretching at the front of the brain. Kind of depending on where you are. In some places it might look a little smashed, but when you compare it to the other, PE1, you can see this one's much more compressed to the front of the brain. And they're very distorted, really, in this case. I mean, if you look at this data set, I think this might actually be my brain. It's not shaped like that. I don't have like a point at the front of my head. If you look through the volumes, then you're actually looking at not time exactly, but you're looking at the different diffusion directions that it's collecting. And as you go through, I don't know if you guys have done that, you'll notice images can look very, very noisy. In this case, this is actually really noisy, depending on the B value. So the higher the B value, the noisier the data set will look. And as we go through, you'll notice this is a multi-shell protocol, so we have several different B values. We have 3,000. Actually, I'll pull it up here so we know for sure. So we have 3,000, 2,100. That seems odd. Okay, need to double check these. This seems a little odd, but 3,000. I was expecting 1,500, 500, and 200. There might be some very strange rounding issues going on in here. But there are multiple B values, and as you run through it, you can kind of see that reflected in the data. Again, with the B values higher, it's noisier, but you have more information on the direction of the white matter tracks. You can kind of see, as you look through the images, if you guys haven't done it already, you'll see there's sort of white lines running in very specific directions through the brain. So as we walk through this, so this is the lower B value, much clearer. This is a very low B value. I don't think it's the B naught image, but this might be the B500. This isn't the best. This really isn't the best data set. But can you guys see what I'm talking about? As you kind of walk through the directions, you can sort of see that there are these propensities for white lines in different directions. In this case, maybe going in that direction in the center image. Let me pull up the other data so it's a little clearer. DTI data is just filled with artifacts, so it's something that has to be kind of carefully controlled for. Okay, so again, this is the first volume, this is the B naught image, this is the PE, I think this was PE0, so we're sort of expecting stretching at the front of the brain. It's really not very stretched here, but you can kind of see it right there. As we walk through the volumes here, very noisy, really. I don't see a lot of what I'm trying to show you guys. But here's another B naught image here. Okay, so top up is taking basically this image that is kind of stretched to the front, and the other PE1, or reverse, as we call it sometimes, which is compressed at the front and generating something that looks more like an actual brain shape. So it's not really stretched at the front all In this case, I did. Yeah. Yeah. So you can see this looks like a brain shape. It doesn't have any weird artifact in it. Let me just pull open command for running pop-up. So in that first data set that I uploaded, you'll find this README text. It's kind of small. If you collect diffusion data here, you probably have run this a million times, but this is sort of our general diffusion top-up script here. So I put some extra information at the top here so you would know that in this particular scan, the p-value on the scanner is set to 3000, although we are collecting multiple p-values throughout the scan, and that the number of directions is set to 102. These are the 2 scans that were actually acquired. And then this is kind of a short description on how to run this. I changed the name if anybody is confused by the fact that this is not what we actually call our top-up script. I just made it up for this class. But this would be very similar, exactly really, to run top-up HCP diffusion, or diff is what we call it, or process top-up for non-multiband diffusion, sorry. All right, this is just a description of the files, a little bit more of a description. Outname, so right here, this is an example on how to run it. You give it the name of the script, which is what we have here. You might actually, in this case, need to do that. It might be an issue some of you have run into. When you run it in this directory, it's not added to your path. First scan, second scan, outname, which tensor file we want to use, and I'll show you that in a second. The number of directions and the p-value used. So that's really how you run it, and that's what I did here, and it's currently running. You can see up here. It's my exact command. I just copy and pasted it from here to there. It gives you an output of what it thinks belongs in the script, the input files, or directions. This is actually a good place to look if something goes wrong, because you might notice something's missing, and if you're running it and it's failing, look right there, because there might be something blank, and then you realize that you either didn't put something in or put something in the wrong order, or you included the .nii.gz on the names of the DTI scans as you run it, something like that. Those are kind of common little issues to have. So the files that it is using, pointed out already, PE1 or PE0, PE1, you're telling it how many directions, 102, and you're telling it the p-value, but you're also giving it this tensor1.dat file. File is on the scanner. It's also in our top-up scripts. So this is I changed it just slightly. I took some comments out of here, but this is something that sits on every scanner that runs diffusion datasets. And there are multiple versions, and depending on which scan you're running, you can tell the scanner to look for a very specific tensor file. Like in the case of what Seraphina is doing, they have very custom tensor files on the scanner. They have to tell the scan specifically, as you're running, look for this file, find the number of directions, and start running through X, Y, and Z gradient information for that specific scan. So here, if you are running a scan with 6 directions, which is the minimum, it would just start here, and this is the information used to tell the gradients what to do in the scanner. But we're running 102, which is way down here. So this is not super helpful. I think Tom might have plotted some of this in one of his classes, but just so you have an idea of where it's getting this information. This sits on the scanner, and in the GUI on the scanner, when you tell it you want to run 102 directions, and you want to use this tensor1.dat file, it will read this file and start playing through each of these. So each line here is representing a volume of your data set. So here you can see it's 0, 0, 0. This is our B naught, so there's no diffusion weighting. So that's our very clear T2 weighted, no diffusion, no extra diffusion weighting image. And as you run through each of the volumes, you're just sort of walking your way down this list of values. And you'll notice that there are other places where like 0, 0, 0. When you get to that volume, it will be another image here. And those images are used by TopUp. I don't know remember which volume it is, but we can probably find it fairly easily. These images are used by TopUp to create basically the shape that it thinks that the brain should be. So it's looking, as TopUp runs, it looks for these B naught images, puts them all together, and basically takes an average of them to apply to the rest of your data. Does that make sense to you? Is this news to anyone, or is this all things that you guys are very comfortable with? New-ish? So I'm going to pull open the TopUp script just for fun. And this is a version, a slightly modified version of the TopUp code that we have. So this is not FSL TopUp. This is our wrapper script around FSL TopUp. So we are using FSL TopUp to run the TopUp correction, but on our servers here, we have our own version that basically gathers the information that it needs. TopUp is written mostly for Siemens scanners. So on our scanner, things aren't quite in the same configuration order that the TopUp program is looking for. So our script runs and grabs everything that you need and puts it all together for you. And then it will just run FSL TopUp. So here it's going through. You don't need to know all of this for the assignment, but it could be interesting potentially. Just so you guys know, TopUp, FSL TopUp requires an even number of slices. So if you're collecting an odd number of slices, one slice has to be removed, or I kind of thought of a better way of doing it, but the current default on our TopUp code actually removes a slice and then runs the TopUp. And you never really get that slice back. But there is another alternative, which I put into a different set of code that actually adds a slice and then at the end removes that slice. But TopUp has to have an even number of slices. So that's what this is doing, is checking to make sure it's an even number of slices and then cutting one off if it's not. Here, looking for the B0 locations and generating these VBAC and VVAL files. And those are the files that once you run TopUp, you'll notice appear in your directory. So VVALs here. And again, this looks a little odd to me. Let me look at the other directory. Yeah, this is what I was expecting to see. I'm not sure what went wrong with that data set. It's okay. I wouldn't worry about it for what you guys are doing. But this is giving you the V value of each volume in your run. So there should be 102 here. There are. And you can see where those V naught images are in your data set. And again, the B of 3000 images will be very, very noisy, and the lower B values will look much more like the images here. So the B of 500 will look very much like a brain, but will not have a lot of diffusion weighting. So it won't be as easy to tell which direction fibers are. And then Bx is just a copy of that tensor.dat file, so it pulls all that information in. All right, so it finds all the B naught images, creates the vval and vvec files, puts it all together for you nicely, and then calls top-up. So it's basically just running FSL top-up, giving it the information that it wants, and then spitting out the output at the end. It's also applying this eddy correcting for eddy currents, and actually this is the older way of doing it. It's not there. I think Alan talked about the more updated version of eddy correct, which I think is just called eddy, or maybe eddy. Do you guys remember eddy? Okay. It does motion correction, and it's much more sophisticated than the one that's being used right here. But anyway, that's sort of the last step in here. What we're calling scripts. So your output, after running top-up using our script, will be slightly different, but you'll have one labeled top-up and one labeled top-up eddy, which is after that eddy correction. Then you have to go on. Let me just pull up the assignment and try to follow that. All right, so we've gone through step 1. Sort of looked at how to produce those images. You could do that in AVNI. Personally, I prefer it. In FSL, I don't know why, but I can't get the contrast brightness how I want it almost ever. AVNI seems to do a better job of just deciding for you. All right, after top-up is done, you want to run the FSL brain extraction tool, which just sort of skull strips the diffusion data, and then DTI fit. And I put the commands in here pretty much exactly as they need to be. Let's see here, that DTI fit commands. Here it is. I was missing it. Okay, so brain extraction tool, feed it your top-up corrected data. It's going to generate a mask, and this is sort of a threshold of where it's going to be clipping. If you end up with a data set in your own research, if you end up with a data set that actually has like holes of brain missing, play around with this threshold setting. I can't give you a great explanation of exactly what that is right now, but play around with this threshold setting. So if it's set too high or too low, you might end up with portions of the brain removed or portions of the skull still on your data set. But DTI fit right here with this command on the eddy corrected data will generate your output that you need for the second chunk of the assignment, which is the scalar data and the vector data. So once you have those after running DTI fit, this doesn't look very nice, but you can generate these images. You pull those up. Anything coming up so far? Anything that's not clear or questions? Okay. One thing I just want to point out again, especially for people who are not here, if you're trying to run top-up and it's not working, this is all you really need to run, but if this script is not part of your path, which it probably will not be, just put a period / in front of it, and that will run that script in that directory that you're working in. I probably should have included that, but it's here. All right, so after DTI fit, you have many more data sets. You have your FA, which is this one here. You have this L1, L2, L3, MD, MO. MD is mean diffusivity. So I know that in Tom's lecture he was talking about the fact that you would expect white CSF because there's a lot of diffusion in fluid and less isotropic diffusion in white matter. So you can see it's darker here. And then you have your B1, B2, B3. We're going to pull up B1 in FSL because Affinity doesn't have the same types of tools. And there are other programs. There's one I played around with a little bit called MR-Trix 3, and you can make some really awesome looking images. I tried to install it on here before the class just to show as an example, but I need to update the operating system first. Right, so you guys probably have spent time with FSL at this point in this course, I would imagine. So you probably know how to pull data in, and honestly, I don't spend a lot of time with FSL, but I'm figuring it out. So, all right, so you can view these data sets here too. The orientation is different. The images are the same. You can play around with brightness and contrast here. And again, I just can never get it exactly how I want it. FSL for some reason. Most interesting one here, I think, is this B1. This is your vector eigenvalue 1, which is the largest, longest vector indicating direction. Here it doesn't look very exciting, but if you go up here and view it as, well, the first image to view would be this one probably. Which is giving you more directional information, but if you view it as a 3-direction vector image line, it starts to look much more interesting in my view. Let me see if I can brighten this up and make it a little bit better. In one of the images you can see in the assignment, there's a zoomed version, and you can zoom right here if you don't know. And here this is indicating the direction of the white matter tracks based on the data that we collected here. So it's showing you every point what direction it thinks the white matter tracks are moving. And depending on the direction, the color is different. So anything going in this direction is red. And you can kind of figure it out here. But I think it's quite interesting. There are programs that produce much nicer looking, like tractography images, where you have like a chunk of the brain cut out and tracks. I'm sure you've seen them. Just pull one up. But this is kind of a nice, quick, easy way to get some of that information. Really, they look like art, honestly. But from this information in a much more sophisticated way, you can get all sorts of great images of the white matter tracks and how everything's in the brain. That's basically it, really, as far as the assignment goes. Once you can run TopUp and DTI-FIT and produce a few of those images and upload them to Canvas, you should be good to go. Any questions about the assignment? This is pretty straightforward for the most part, other than waiting 4 hours for TopUp. Okay. Does anybody actually run it and how to finish? Not yet? Okay. All right. Well, it runs faster on servers, but I was expecting it would run pretty fast on like your own PC as well, because it doesn't have as much of a load on it, but apparently it's very slow.
Do you know how long it takes on a server?
Well, it depends on the server, but which server do you use typically?
I use the Neuro Compute ones for my lab.
Okay. Oh, this Rince's lab.
Yeah.
Yeah, I think you guys have pretty powerful servers. Maybe 20 minutes.
Okay.
On here, it seems like it's probably going to take more like 2 hours or so. If it just doesn't finish, or if you have a major issue, you could, if you can get it to run and sort of show that you were able to get it to run, but it's just running forever, it will finish eventually. You could just use the other data set to generate those images. That should be fine. As long as you can go through that process, I think you should be fine. That's it, I guess. Anything else? Okay. Anybody running into issues? Viewing or running any other commands? It's too easy. So I'll just let it run. See how long it takes. I tried installing DSI Studio on here as well, which is something Alan likes and uses. It installed very easily. The interface is a little odd, and I just didn't have time to play around with it. But there are a lot of packages that you can use that could potentially be more sophisticated than FSL, especially what we have done so far. We haven't done any group analyses yet either.